So let's begin from where we left off last lecture, right? So we looked at the governing equations, right? And what we're going to do is sort of briefly or kind of outline the method, okay, the numerical method with which we are going to go and solve something like this. And this method is primarily what Moretti outlined. So I gave you the reference for that. So I'll just basically outline the procedure in which this can be done. And let me reiterate that the best way to learn this or understand the numerical method is to really implement it, right? Write a computer program and implement it. So what I will do is basically go over the method, and then, like I said, I've pulled up a more recent paper, right? And it has some. It's a CFD work, so it has some nice, colorful pictures. They always make for good reading. So I will just show you some of the results, which you might get during numerical analysis. Okay. So now let us. So go ahead. So what we have here is our cone at an angle of attack, right? So this is our free stream, okay? This is our free stream, and okay. Right. So this is our cone at an angle of attack. This, and this is our alpha, right? So and we will have a shock structure somewhere like this. Right. So this is our shock structure. Okay, so let us. How do we, sort of? So this is our problem. This is our problem. So we have a cone at an angle of, which is inclined at an angle of attack of, say, alpha with the oncoming supersonic free stream. We need to calculate the properties. And what are the flow properties that we are looking at? The 7 properties that we talked about yesterday. 7 why? Because we are looking at spherical coordinates, right? So the velocity components and the thermodynamic properties, right? So that's what we are looking at. So how do we go about this? Okay, so now I'm going to sort of, based on this, you can actually develop a skeleton for a nice computer program, and then slowly try to implement it. Okay, this would call for an assignment, which would, for first-time programmers will take a little more time, but as you get used to it, you kind of get a hang of the whole thing, right? Okay, so the way we are going to do this, you have seen we wrote down the equations in the spherical coordinates. Okay, so the way we're going to start this is by assuming a flow properties, and then march forward from there. Okay, so first step is so assume the flow field on a spherical surface R0. What does that mean? Let's come back here. Okay, so what this means is that, okay, so this is the vertex of this whole whole thing, right. So, we have various radii extended from that vertex. Some of the radii form the surface of the cone, the other radii form the surface of this shock structure. So, let us consider, okay, let us consider a surface which is within the shock structure, which is between rather the shock and the body, right. What does that mean? So, you have two concentric cones, okay, use two concentric cones. You remember when we did the green and the blue, so they were basically embedded cones within the red one, right. So, let us take a shock, okay, let us consider a shock structure, say, which is inside here, like that. So, this, okay, we are going to draw it like this, and this radius, okay. So, this radius here, okay, this is r naught. So, this radius is r naught. Okay. So, what we are going to do is assume the flow field on a spherical surface r naught. We are going to, so if you have a, if you can think of a cone, right, which is embedded within this shock structure, which is between the shock and the body, right, the radius of that is r naught, then we are going to assume the flow on that, right, as we start, okay, we are going to when we start, okay. Yeah, well, this is the assumed flow is non-conical. Okay, the assumed flow is non-conical, but and you can really be arbitrary when you assume flow out here. Although there are two conditions that have to be adhered to, which is the conditions which are like required conditions. Okay, say required conditions. Okay. Local enthalpy should be equal to the free stream. Okay. So, local enthalpy should be equal to the free stream enthalpy, and the mass flow rate through r is equal to r naught. Okay. So, total or integrated mass flow. So, total mass through, okay, let me write it this way, integrated mass flow, okay, through, okay, is equal to the free stream mass flow by the spherical surface. Okay. So, this is non-conical, the flow field that you assume on this r is equal to r0, and it can be arbitrary, but number one, local enthalpy should be equal to the free stream enthalpy, and secondly, the total mass flow through this cone, right, should be equal to the free stream mass flow, which is intercepted by this conical surface, right. Now, next is step 2. Okay. So, having done that, this is the first part where we assume the flow, right. So, step 1 basically consists of begin by assuming a conical surface within the shock and the body and assume the flow on it, okay, which can be arbitrary, but these two conditions should hold. So, that takes care of your step 1. Okay. If you look at your governing equations, it has all the derivatives. Okay. It consists of derivatives, for example, del v phi, del phi, right, del v r, del r, then del V r del phi, so on and so forth. So, how now we know the flow field at r is equal to r naught. So, that is known. So, okay. So, now we can calculate the derivatives with respect to the phi and theta, right. So, phi and theta directions using finite differences. So, then derivatives okay. So, now the derivatives, like I said, okay. So, del phi del v r del phi del v theta del r and so on and so del phi del theta. So, all the derivatives, if you see your governing equations, to solve this governing equation, which is the equations basically 4 to 10 that you have. So, to solve these equations, okay, the continuity equation, so on and so forth, we need for example, the continuity equation. Just to give you an example, the continuity equation has this term. Okay, it has this term, then it also has this term. Okay, then the momentum in r direction, for example, it has. Okay, so all these terms, okay, all these, so phi and theta. So, the derivatives in the phi and theta directions are obtained by using finite differences, right. Now, so, when I say finite differences, so obviously you will have to need, you will need to have you know, a basic idea of what I mean by that, right. So, it could be you know, you could basically go over what you have learnt before in case you are not familiar with what I am talking about. So, take a very basic book and very basic finite differences, what that means, okay, is something that you should be able to figure out. So, having done that in here, so now we know the derivatives. Okay. So, then if I do that, so clearly if I am able to find out the you know, derivatives, then if we use the equations, the governing equations, the continuity, the momentum in r, theta and phi directions, the energy equation, we use all of that, which is 4 to 8, 4 to 8 or 4 to 10. Okay. I do not remember how I named them. Yeah, 4 to 8 actually. So, 4 to 8, so which contains all our equations, the energy, momentum and continuity, right. So, using equations, using the equations which we derived yesterday, or 4 to 8, okay, we therefore, if you look at those equations, they give us, okay, they give us these. So, the continuity, for example, so we obtain what we obtain is, if you see the continuity gives us, this, okay. Oh, sorry. Right, the continuity gives us this, momentum in r direction gives us this. Then momentum in theta direction right, and what else, and we get h, okay, and we get so these are the stuff that we get. So, these are the derivatives that we are able to get. So, having calculated the derivatives in the phi and theta, how do we get this? We calculate this using finite differences, using the values which we have assumed, okay. And once having done that, we put those derivatives into these equations 4 to 8, okay, and we obtained these derivatives. Okay, you can clearly see that these derivatives are in the r direction, okay, are in the r direction. So, these were in the phi and theta plane, which was defined by the radial vector r naught, which we assumed. Okay. So, therefore, now what we will do is, okay, since if you remember right, so we came up here, this was an arbitrary assumption, okay, we did not know about this. So, we just assumed, we took an r and we assumed a set of values over here. Now, we need to march these values further in these direction, in the r direction, okay, because this r is not something that we know for sure, we just assume that. So, the next step of course, is that we march the solution in the r direction. So, if I say come here, okay. So, let us call this okay. So, essentially say if I have if I go say delta r in the direction of r, how will my properties be? Okay. So, now the way we would sort of do that, for example, let us march the say density, okay, the density which we assume that r is equal to r naught, let us march it into r like the next r that we would assume. So, which is say density, okay, okay, okay. So, let us just try and understand what this means out here. Okay. So, if you look at this, if I march the solution in the r direction. Okay. So, what I am saying here is that the density here, I mean this could be any property here, which could be out of the 7 the density, temperature, velocities, etc. Now, if I have the density here in the at r, okay, so the density at r plus delta r at the next radial position, okay, is equal to rho r, okay, plus del rho del r average into delta r, which is the variation, okay, the variation of this density as we go from r to r plus delta r into the total change in delta r. This is the whole idea. So, let me sort of try and clarify that here. So, we are going from r naught, okay, we are going from r naught to another r. So, let us say we are going, so let us just forget about this, let us forget about this r naught for a while. So, let us say we have, so let us call this as say r1, okay, let us call that as r1, and let us call this as r2. Okay. So, what we have done, okay, so what we have done here, okay, is that, see, if you look at r1, if you look at just this particular radius of curvature, if you look at that, okay, and if you project it, right, if you project it, it is a particular circle, right, on which theta and phi will vary, on which theta and phi will vary, is not it? The r remains the same. Okay. So, that theta and phi variation is what we calculated using finite differences. And how? Because we assumed the flow at r is equal to r1. That is how we started. Okay. Now, having done that, what we have found out is the variation of properties, is the derivative of the properties in the r direction. right. We found that out. So, we using our governing equations. So, now we want to move from, say, if I have predicted it, if I have calculated properties in, say, at a radial distance r1, I want to move to the, say, if I want to look at properties which is further down, then what do I do? Okay. Now, what we are saying here is that if you look at this particular picture here, is that if you look at this, that the, say, density, okay, density at R2, okay, density at R2 is equal to the density at R1, okay, density at R2 is equal to density of R1, okay, plus okay, the average change of density over R, the average change of density over R, okay, into delta R, and that delta R is nothing but this delta R. I think this is easy to visualize, isn't it? So, we have properties here. Okay. So, what I am saying is the property here is equal to the value of the property here, plus if I take an average change in the rate of change of the property in the R direction, okay, that into delta R, because that's the difference between R2 and R1. Okay. So, that is what is basically my step 4. Okay. Now, in here this delta rho delta R, what we have calculated in step 3 is basically these values. We have calculated delta R, del rho and del R here. What we are looking to do here though is del rho del R, an average value. What does that mean? Okay. Now, this here actually, this term, okay, now this term out here, okay, so this term out here, okay, now this is calculated So, this term out here is calculated using a predictor corrector approach. Okay. Now, let us just see what that means, this average value. Okay. Now, using say the continuity equation, okay, we calculate the predicted value using forward differences in theta and phi. Okay. So, for example, okay, so number 1, okay, we calculate, okay, okay. What is important here is number 1, we do 2 things. Okay. So, calculate the predicted values, calculate or rather predict the values using these forward difference. Okay. We will use forward differences, okay, forward differences in theta and phi. Okay. So, we will predict a value, okay, at a particular point. Okay. So, how will we do that? You see, we have this, for example, del rho del R here. Okay. Now, this is available to us. This is available to us. So, now using a forward difference, okay, in theta and phi, we calculate the predicted values. We just use these predicted, we predict the values using forward difference in theta and phi, and let us call those values as, let us call those, just call those values using a bar like this. Okay. Okay. We are going to call this we just we calculate the predicted values using the forward difference theta and phi, and we call this as this. Okay. And again, now using these differences, okay, again, okay, we calculate the corrected values. We use corrected values using backward differences in theta and phi. So again, the second thing will be, okay, so let us say here, okay, let me just write here. So using backward differences, okay, we use backward difference, okay, to calculate the corrected values. So when we come here, so we use now backward differences, okay, we use backward difference, and that gives us the corrected values. So we will calculate the corrected values, right, in this fashion. Okay. So once we do that, okay, once we do that using this, then we will calculate this, for example, del rho del r average, okay, as an average of this predicted and corrected values, which means what? Which means this, which means that this is basically equal to, okay, okay. So the way, again, let us just sort of dwell on this a little more. So we need to calculate the rate of change of this property as an average, okay, using a predictor corrector approach. So what we do here is, okay, we use a forward difference, okay, to predict the values, and forward differences in theta and phi, okay, and we calculate the predicted values. Let us call that as this. Then we use for the same property here, we use a backward difference, okay, and calculate the corrected values. So you can sort of crudely saying it's like using two different approaches, okay, you get two different values for the same property, and hence you get an average, okay, an average for this change in rate of change of that property as this. Okay. So this is the predictor corrector approach. Okay. This is also again in a standard book or explanation. This is sort of something that you can just look up in case you are not familiar with this. Okay. If I have time, I am probably going to go ahead and explain on that a little more. Okay. So that's the predictor corrector approach, right. So okay, so once we so that's it. So in this, so we then march the solution in the r direction. Okay. So how long do we do that? So how long do we do that? Okay. So we have come here and we are now calculating. So what I did just now here is this average value. Okay. So this average value, we said we will use calculate this using a predictor corrector approach. Okay. We will do that. So essentially now what I will get, the whole objective of all of that is to get an estimate for this rho of R2, for the density at R2. Okay. Now I started out by assuming this, which is in no way the correct value, which is not the correct value. So therefore, I am trying to get a value which is on which I will be able to converge. So therefore, slowly what we will see is that the difference between say rho R2 minus say rho R1. Okay. So if I were to call this as say difference, or say let me call this as say this is equal to delta, right, or yeah, so let me call it this delta rho r. Okay. Now, slowly what we will see is that our approach here will basically be that this delta rho r approaches 0. Of course, when you are writing a computer program, you are going to say it is within a certain tolerance, and that tolerance is something that you design. Okay. So, it could be 10 to the power minus 10 or whatever, so however you want your things to progress. And so, slowly what we will see that we will be able to correct the error that we made in assuming it to be R naught. Okay. So, as we proceed from R naught to the next one, okay, so we see how close we are to what we had assumed. So, which would mean that this the distance. So, finally, what we will have is that we will converge to a R. Okay. So, say this R was incorrect or this R was incorrect. So, we assume another R. So, say we come over here. Okay. So, this was say this R 1 actually say moves to say R 1 dash, okay. But then R 2 also moves say somewhere right here. R 2 also moves say somewhere over here. Okay, so, this is your say R 2 dash. So, if you think if for you if R 1 dash and R 2 dash are close enough, okay, if you do not see much of a difference here, then your solution is converged. Okay, so, this is a solution that you will take. Okay. So, that is basically the numerical procedure as we know it. Okay. So, okay. So, like I said, this method is basically illustrated, started out by Moretti. So, I have given you the reference for this. For details of it, you will have to go through that. Okay. Number one, and secondly, I think the only way to really understand this is to implement a computer program on your own. Okay, I think that is really necessary, as it was necessary for the conical flow which we did in the axisymmetric case also. Unless and until you do it, it's difficult to understand. Okay. What I'll do now is like I said, I pulled out a paper which is more recent, 2009 I think, and we will look at some of the, it's interesting, some of the results that are there are sort of pretty interesting. Okay. All right. So, let us say look at this. Okay, so this is the paper that I am looking at. Okay, this is the paper that I am looking at. So, okay. Okay, so let us look at this. So, this is the name of the paper. Okay, so this is the name of the paper. Oh, shoot. Okay, this is the name of the paper. If you have to look at this, okay, asymmetric vortices around a body in a high angle of attack, supersonic flow, right. So, and it is in this particular journal. Okay, this is in journal of, yeah. So, it is in 2009. Okay. So, what I found interesting here is some of the results, because they make for nice pictures, and I think pictures are a nice way to see things. So, you can download this paper for yourself, and yeah, I think this should be enough for you to get a hold of this particular paper if you already do not have it. So, this should be enough for you to know. Okay. Okay. So, let us just look at this thing. Okay. Let us just look at this. So, I am not going into details as to how they have calculated and things like that. I am just going to show you the pictures as to just to give an idea what sort of numerical results are we looking at. Okay. How will these results look like once you get, because it is very difficult you get a bunch of numbers, I mean how do you interpret those? I think that is the most important question, right. So, for example, look at this picture here. Okay. Let us look at this picture. So, this is essentially their, so if you look at this, this is the for the cylinder that they are considering, which is like the ogive cylinder that they are talking about. So, you can see here, right, you have a pointed nose or cone. So, it is similar to what we have been studying so far, isn't it. So, if you look at this, so this the L is 10D. So, this D is basically this whole this length out here, isn't it. So, if you look at it, this is the entire length. So, this D is given, and this is Ln, I think, which is 3 times the D, okay, 3 times. So, from the cone vertex to the bottom, I guess, okay, to the base is 3 times the D, and the entire length is 10 times this diameter, if you will. Okay, after all, it is a cylinder. And okay, so this is it. All right. So, this is the geometry that they are considering. Okay, and this is a picture of how their mesh looks like. Okay, this is a picture of how the mesh looks like. So, the grid system. Okay, this is the grid system. Okay. Okay, so this is the so that is the grid system. Okay, and if you look at this, this is what I was talking about. So, okay, so right. So, if you look at this, so this is how the grid looks like, right. So, this is how the grid looks like. Okay. Now, here I would like to point out, actually, although you might be knowing, this is typically done. I mean, for all those of you who are new to CFD, computational work, and so on and so forth. So, you can see that you have got really like dark regions around here. You see these dark regions out here, and then you seem to have these this is actually called a mesh or a grid or whatever, right. So, you can see that these sort of rectangles, okay, have fanned out quite a lot. It's, I mean, these are quite large once you get away from it, but here it is pretty congested. Now, this is a very typical thing to do, isn't it? And it makes sense to us, doesn't it? Because and if you remember the analysis that we did, that as we go farther away, okay, farther away from the from the wavy wall, if you remember, right, using the linearized theory, what happens if it is a supersonic flow? Does it do the disturbances die out? Okay. So, here too, I think the reason we have more and more congested mesh around the body or near these edges, especially the sharp ones, is because we do not want to miss out any information. So, there is a lot happening in a small little place, or these nooks and corners, and we do not want to miss out on any information. So, this is the grid is what is going to give us the information. So, something for analysis on a grid based method is about that. So, we have to really position our grid in such a way that we get the information that we are looking for, right. Okay. So, having done that, so having done that, let us go and look at some of the results. I thought Okay, so this is interesting. I think it's so if you look at say figure 5 here, figure 5 is what I am looking at here. Okay, let's see if I can get this up. Okay, so can't do it. Okay, so if I am say looking at this, right. So, for example, okay, so let's say, right. So, we are looking at this. Now, this is they are looking at 3 types of grids basically. Okay, so grid 4, grid 5 and grid 6 over here. Okay. So, this comparison of streamline, that x by d equal to 7.61. What does this mean? What does this mean? Okay, x by d equal to 7.61. So, let us go back to the first diagram here. Okay. So, if you consider x along the length of the cylinder, okay, length along the cylinder, then so at some position x, okay, so if x is 7.61, if x is 7.61, okay, times the this d, the diameter, that is what x is equal to, x by d is equal to 7.61 means. Okay, if you look at this. So, x is equal to 7.61 d. So, if you start from the vertex of the cone, then you travel basically 7.61 d. That is a section of the conical structure that we are looking at. So, if you look at that, so what this is showing is 3 types of grids, and they are showing the solution here. And you can clearly see, the difference between the 3 cases here. Let me just point out a few things. Okay. So, you can see that we have these 2 vortices out here, large circulation here, 2 here, we have the same thing. We have this is much closer together, we have a large congestion, which means that we have like really dark areas out here. And again, if you look at this here, so we have 2 of these vortices which are pretty pronounced, and which is pronounced mostly for this grid 6. Okay. And we can see that in grid 5 as well, but this is not that pronounced, at least the second one is not pronounced. So, this is how basically you change your grid, etc., to see what sort of solution we are looking at. And I think what these sort of lines, these 2 sort of lines are looking at. Okay. Okay, I haven't read the paper in full, but I would think what they are looking at is to comparing the sizes, okay, of these 2 vortices over here, which seems to be growing. Yeah, which seems to be growing, but I think this has a more congestion. The grid 6, the C, it has a lot more congestion of streamlines over here, and that is expected. You have a larger grid system, so that is what you would have. Okay, so I am not going to go here. Let us go and look at some. They have some real nice. Okay, yeah. Okay, so this is the one I think all of you will like. Okay, so a comparison of entropy contours at x is equal to x by L, okay, equal to 0.97. Okay, and for different angles of attack. It's a very interesting picture, isn't it? So, if I were to look at this, let us see if I can bring this up here. Okay. So, if I do this, okay. So, there we go. Okay. So, what we are looking at here, now can we go back? Okay. There we go. So, okay. Now, when we say x by L is equal to, when we say x by L equal to 0.97, what do we mean? Okay, let us go back to this figure here. So, L is this whole length. So, if I take x along this, so I am almost like to at the end of it. Okay, I am almost to the end of it. So, it is nearly the at the edge that I am looking at. So, if I go down here, so if I look at this picture here, okay. So, this is the, so now what you can see here is very interesting. Okay, what you can see here is pretty interesting. Okay, let us keep it at that. Okay, so now what you see here is that as you look, this is angle of attack is 10, right, and this is the angle of attack is 22, angle of attack is 28. So, we really increase, there is a quite a large leap from 10 to 28, nearly 20 degrees leap. Okay. And you can see the difference, you can really see the difference in the entropy contours over here, and then the change of the entropy as we do that. And what is more important, I think, which we sort of were discussing in the first couple of lectures, okay, when we started this, is the how the vertical singularity, how that vertical singularity moves away from the body, okay, as we increase the angle of attack beyond the theta c, isn't it? So, I think you can sort of see that into play over here. So, you have an angle of attack of 10 degrees. Like I said, I have not sort of read through this paper. So, I do not know whether this is less than the angle of attack, this is the less than theta c here, but you can see sort of, you can sort of think of this point still being attached to over here on the body, and then you see this, you come here, you increase the angle of attack, and also you see a lot of asymmetry. The asymmetry is very, very obvious. Okay, this is the entropy, and you see that here. Okay, and then you come over here. So, you can see these two, okay, these two sort of loops of this entropy here, and then you see this point. So, as you increase the angle of attack. Okay. So, okay, and then if I go down here, okay, so if I okay, so if I go down here, so what again, so okay, this is also another nice one. So, this is again, so the what we saw just now is at the same location, and if you change the angle of attack, and here we keep the angle of attack the same. Okay, so this is the picture where we keep the angle of attack same, angle of attack is 28 degrees. So, it is very highly skewed, so to speak, with the free stream. So, you have a angle of attack 20, and we are looking at the entropy values moving along the length of the cone, right, which is what is shown over here. So, if you move along the length of the cone, you can see how the entropy is varying, or how is it changing, right. So, three little these sections are given here for further look at it. So, I hope you understand. So, this is how we look at it, and these three pictures down here is if I look at it from here or from this side, right. So, if I look at it that way. So, you can see here that as we move along, as we go further downstream, on this cone, right, the asymmetry increases, and we have a larger asymmetry or larger changes in entropy. Okay. This is what we see over here. Okay. And this is yet another one. Yeah. So, we looked at the change in the length. Now, what we will look at this is if we change the incoming Mach number, right. You see, if I can see the same large changes entropy, if we change the Mach number from 1.4 to 2.4, even that also is quite an important change here. Okay, so I think we will end on that note. Okay. What we will do next class is the supersonic flow past a blunt body, because that again will have its own speciality. We will talk about that in the next class. We will stop here, okay, and hopefully this gives you at least a start up onto what we are talking about in terms of 3-dimensional flow field. Okay, thank you very much.